Okay, so this is about P4TC and how we integrated eBPF into it. Anybody heard of P4TC yet? Yes, good, good. I know you did, Shrijit. Okay, so so there's a big history behind this. The first guy that ever showed up was Marty Kadosh from NVIDIA. He showed up with P4, and we just laughed him out of the room. Basically, until 2021. So we've been working on this for about 2 years now. So there's some history, basically, and eventually, you know, people may laugh you off or laugh you out of the room, but at some point, you know, they listen. And I have to say, there's a lot of things that have changed in the P4 community. A lot more people are producing hardware that does P4. There's the vendors are specifying specs using P4. So there's more. Maybe the time was wrong when Marty came over. But there's history, basically. So last year, in the last Netdev, we presented our approach on how to do P4 over TC, and that's part of history now. Why are we doing this? Is mostly to grow programmability ecosystem. The Datapath using P4 with a Linux native implementation. I would just want to take a jab at DPDK. That's an old nod. Say Linux is not DPDK. There's plenty of software versions of P4 that run on DPDK. So what happens is you start with your P4 program, and you run a compiler. Tom was saying network developers need to learn about compilers. So you generate your eBPF code, you generate a template, you load it, ready to go. This reduces a lot of developer dependency. We don't need geniuses. Can I claim I'm a genius? You don't need me for TC anymore. You don't need who's a guru at eBPF here. We don't need eBPF gurus anymore, right? Of course, you'll have to debug the problem, this solution, etc., when something is not obvious. And we don't have to upstream. You write your P4 program, we're going to upstream once, and then subsequent to that, you write your P4 program. That is the language you use. You run a compiler, and out comes the necessary artifacts. Right, so why P4? I'm just going to skip this, but there is a momentum. I think probably I should focus on that last bullet there. To each their each. That rhymed, I think. Conway's law, right? Everybody builds a data path that looks like what their what their applications would look like. You know, if you go and look at Google's versus Azure versus Amazon, everybody implements similar things, different approaches in the data path, right? So this should allow you to say, I'm just going to do my own data path. I don't want the 20,000 knobs that the bridge code has. I just need 2, right? And you can go ahead and implement it with P4. Why Linux kernel? I claim it's the mother of all networking infrastructure. I don't think anybody would disagree with that. If it beeps, it probably runs Linux. If it has LEDs flashing, maybe emits some smoke, it has to be running Linux. And one of the goals is to avoid the multi-vendor approaches to how they would implement P4 using proprietary APIs that are vendor-specific. Most people claim that's vendor lock-in. And a few of the larger organizations would source from multiple NIC vendors. So we want a singular API, right? And with TC, you get the same consistent infrastructure. Although this talk is not about hardware offload, it's the same infrastructure for software as it is for hardware. Okay, so I'm going to skip the rest of this just to get to the point. Okay, so that mouse works, yes. So you start with your P4 program right there. If you're doing hardware, there may be target architecture specific constraints, like, you know, maybe how much TCAM you have, etc. You run this open source compiler called P4C. You pass it an option to say, I want P4TC backend. It generates, I'm sorry, I should say this is the old way because I'm trying to build the context for history. So in the old ways, it will generate what we call as an introspection file. Think of this as sort of a name to ID translator for command line objects. And then it builds several objects. So in the past, we had a pipeline, a tables, actions, metadata, parser, and extends. You take that, it's a shell script, you run it, and it loads into the kernel. Now you have sort of manifested the equivalent of a P4 program in the kernel. And that's it. It's like you've loaded the program at this point. And the data path essentially looks something like this. So the data path, that manifestation of the program, essentially builds something like U32 or pEdit. Are people familiar with what U32 is? On this side? Yeah, so it's basically an offset, a DSL that describes offset length values to match, and pEdit will also use the same language, but to say what to edit or how to edit something. You can say, go to this offset, replace the U8 with this value after you mask it with these values. A lot of people that complain about TC are probably not too happy with the U32 lingo that's used. That's the biggest complaint normally is U32 is so complex because they've looked at TC is so complex because U32 is complex. It is complex, but if you know how to read bits and bytes, it's beautiful, right? I did give a talk on it in the Prague Hex 2019 session if you want to know about P32. It's my favorite classifier. Flow is not my favorite, it's U32. pEdit, but I'm biased because I wrote pEdit. And so what we did is, if you go back to this slide, is we figure, okay, there is no need to change the kernel. I'm just going to generate code that does parsing, does matching, does actions, using something that looks like U32 and pEdit, which has been around for over 20 years. Okay, so that looks great, right? So a packet comes in, as before, it hits TC. We're only focusing on TC. You run your engine, which is a U32. You run your parser. The parser at that point was called kparser, which came from Tom's team. You then take the result of the parser, and you can now do match actions using a U32-like language, and you can do a packet editing in a pEdit-like language, right? So, and there's table lookups. So all the objects, you'll be looking them up in. It was a beautiful architecture. Then we posted on the list, and oh my God! So the eBPF people came out and said, "Don't do this, right? Use eBPF." Why eBPF? I think probably the best reason that was given was security. That if you run the verifier, you get to win. And people cited examples of the parser, for example, in the past had CVEs, good reasons, and you get better performance. Now, we actually went and tried to validate this. We presented at the P4 workshop in 2023, the results we found. And it is true, eBPF does give you performance improvement with a caveat. The caveat is if you're really using P4 in the native domain is supposed to be used, you really have more than one table. You may have ternary tables. And performance really, at some point, there's no difference between our scripting approach, between eBPF, and whether you run eBPF in XDP versus in TC, because XDP is supposed to be a much more performant spot for eBPF. There's no difference, really. Once I starting having like 3-4 tables in series, the difference in packets per second output, whether you run an XDP or eBPF, is very minimal. It's noise, basically, right? But nevertheless, for the simple cases where some people would want to do 1 or 2 tables, eBPF does give us performance improvement over our scripting approach. What we lost as well is the operational simplicity. So if you look at this approach here, this is just a shell script, right? I can email you this script and say, okay, go and run this. And now you have a Datapath that will do your packet processing, basically. I can't do that anymore. So what's the new approach? And of course, we compromised and said, we are happy, we're working with communities, and all that. So just remember, if people are fighting on the mailing list, if you reach out to them in person, they're much more amenable to listen. We listened to each other. We had communication with several people. I'm not going to mention any names, but there was some good discussions. The one thing I should mention is that we actually had tried to do eBPF before we started with our scripting approach, and there were some challenges. It was impossible to have every set in the P4 language to run as eBPF because of Turing completeness, right? Because of Turing completeness, the verifier, you basically had to really wrestle with the verifier, and we thought, okay, we don't want to lose that operational simplicity because somebody just generated eBPF and they had to spend 10 hours trying to see how they can trick the verifier to pass pointers. So what changed? Well, we now have access to kfuncs. So I can actually call inside the kernel proper with kfuncs. That made a huge difference for us and how we moved forward. Okay. So what's the new workflow? So you can see that now we're generating, the compiler now generates eBPF code. It generates two pieces of code. One is a parser, and one is the control block. How many people are familiar with what P4 looks like? If they saw a P4 program, okay, so 1, 2, okay, maybe 1%. I'll show an example after. Right, so if I was to break it down, there's a piece which describes the packet, how your headers look like. There's a piece that describes how to parse it. And there's a piece which describes how to, let's say, iterate through it's called the control block. It describes, okay, first you look up this table with this key, and if you find it, you find an action, then execute the action. Or look up these 10 tables, and then at the end, you execute the actions. And if you're to edit packets, you do them at the end as well, right? So we're generating basically the parser now and the P4 control have been removed from here, right? The control and the metadata is gone. It's now part of eBPF. So anything that required computation is gone, right? The challenge is now, well, there's no challenge because we output a makefile as well. So there's a makefile that gets generated, and the eBPF programs. I'll show some quick samples after. And you still have your script which manifests the program in the kernel. You load it with netlink, you compile your C program, your eBPF, you load it using TC. Okay, I'll show some samples after. Okay, this is your new data path now. So now you can see the kfuncs that are, so there's a kfuncs to do any object that requires control plane has to go through TC. So you do, if you're familiar with registers in P4, then they'll go through that. The parser is sitting here. The objects that require control time update are running through netlink as before, using CRUD operations. So standard TC, well known, well understood. We're using TC, just IP route to TC. Nothing magical about it. And anything else is kfuncs. XDP, and so you can actually generate XDP code and or TC code for eBPF. So you can generate both, and basically the packet comes in. The parser could reside here, for example, or you could do some pre-processing of the parser, pass the metadata result from the parser to here, and then you do your computation, do any lookups, any table updates, etc., through the kfuncs. Okay, so this makes it very simple for us to extend this to do extends. I don't know if you're familiar with extends. In P4, extends are equivalent to helpers. So extends are now kfuncs. You can call any kernel code, or you can write some new kernel code and just invoke it through kfuncs. Any questions on this?
Oh, I have a question.
Yeah.
So what became of the TC scripting? Is that still part of this, or is it all?
Yeah, it's still there. It's still there. It's here. Right? But there's some pieces that have moved. The parser has moved, for example. The metadata has moved. The control block has moved. If I'll have to show you a P4 program to make sense of it.
Well, I guess what I'm getting at, so is the data path completely in eBPF with the K-funcs, or is there part of it not in eBPF and part in eBPF?
The software data path is totally in eBPF.
Right.
Right. Willem, sorry, go ahead.
What about the rest?
The objects are still in TC because we want to use IP route 2 and netlink. That's well understood.
Right, but that's the front end. So there's still an engine. So we're still going through TC, the normal TC for the match action, right?
No, okay. So maybe I'll show an example. The lookups, the tables, the algorithmic TCAM, we implement an algorithmic TCAM, is still sitting on the TC side because you can now control it through through netlink, right? So let's pick a simple object.
Yeah, I think it's the separation between control plane and data plane that's kind of confusing me.
Yeah.
And my simple question is the whole data plane in eBPF?
Absolutely. For the software, right? If in the future there's a hardware offload, and there's going to be a talk after this on some hardware offload. Okay. I'm not doing it. This is not to do with hardware offload, although I have a slide at the end to show.
Yeah, that's a separate story.
Right.
But so the feedback from the list was try to use eBPF, and you've done that.
Yes.
That's fantastic. But you've maintained the interfaces to use P4TC.
Absolutely.
Okay.
I mean, the control plane, I'll be crazy to replace netlink with another control plane.
Yeah, the K-func. So you add new K-funcs, is that right? To access these P4 objects?
About 2 or 3 K-funcs.
Okay.
Right, that's it. Okay. We have one that actually, well, I say like a handful, maybe 5. Yeah, the extents have nothing to do with that, though. Yeah. So just tables and things like registers. I don't know if you're familiar with P4. Those are the only things that we're upstreaming.
So they're P4 specific K-funcs. They're not like TC specific. Okay. I mean, I can see the eBPF argument. Like we have eBPF maps. So we're going to use TC data structures. It will probably still be a bit of a hard sell, but you have to really explain well why, from an interface point of view, that's just.
Or if you can show me how to do.
Well,
so if I can do maps with netlink, because I have to use netlink, like I said, I'd be totally crazy not to use netlink.
Okay, sure.
Right, and I don't think that's. I think that's like.
No, but that's the argument. That's the answer, right? Like
you're
wedded to netlink for your application.
Yes,
and that's sounds reasonable to me. But I'm pretty sure that the remaining point will be the data structures are different from the data structures people usually would use from eBPF.
Right.
So I'm curious what I would like to see the real K-func.
Yeah, maybe I'll show one.
All right, thanks.
Right. So it's, but yeah, we are not gonna. You're gonna have to kill me to get me not to use netlink.
One other question.
Yeah.
What's the JSON at the top?
Oh, JSON is just something the compiler generates just when you're using IP route 2 to Stephen and David. Where's David today?
So is this just for like debug output, or is this used operationally?
So because I'll show an example, but it's just sort of think of it as a name resolution, name to ID, because what we send to the kernel here is IDs, right? It's binary data. But when humans type destination address, IP destination address, that object, when that IP space destination address is in English, right? Or whatever language you choose. So we will then look up what is this IP address ID is by querying the JSON file. And you say, oh, it's ID number 3. Then we'll create our TLVs with ID 3.
Where does that happen? That's in the
user space
P4TC program?
Yeah, so you can write your own control plane, but I'm a big fan of keeping things up public, like with IP route 2 instead of writing your own program. So we are just gonna, it's just a small extension to to IP route 2. We have code, I'll point the link afterwards.
So I'm a bit confused as well with the use of TC. It's just for the front end. My question is, you talk about implementing TCAMs by software with the tip. Are you going to talk about that? How the match and action is being processed now with eBPF?
Yeah, I don't know if I have time, I will, but yeah, or we can talk about it if you want to see the code.
Okay.
Yeah, think of it as an algorithmic TCAM because that's what the P4 spec says. You can have exact matches, ternary, LPM, ranges. If you're to implement an FPGA, that's how it would look. We've tested it against the eBPF maps, by the way, and where in some cases we're better, in some cases we're equal, right?
So I've been working on projects on the Tofino stuff, and Intel's code generates the emulation that runs on the x86 stuff. Have you checked to see how that works from yours compares with theirs from a performance perspective or anything like that?
Yeah, I'm pretty sure, without a doubt in my mind, we'll beat their performance because most of these guys tend to generate like a JSON engine to try and do a data path. At least there's something called BMV2. I don't know what Tofino uses, but if you look at Microsoft and how they emulate this, they would run BMV2. I think hopefully somebody will correct me if they're online that is more familiar with Dash. Microsoft gives you specs, and then you as a vendor, they give you specs in P4, you test them in software. They will test them, right? So actually, because I don't think I have much time. Let me run, and then we can take this. So here is our control plane API, right? So we are more not RPC based, but more sort of CRAD based. So all the commands have a verb. A verb could be a create, read, update, delete, which is followed by a noun, which points a Unix-like path to the object. So for example, here you can see that I'm doing a get to my program. There could be multiple programs installed, to a table that's called my table, and I'm going to look for this IP destination address with this prefix and a priority of 16. So to answer your question, Tom, this is what we will do is, you see, these are English names, or they're human representation, and that's a human representation. So is this. We will go and look it up in that JSON file. Say, okay, can you translate this to me in? Give me the IDs for these things, and I'm then going to take that and build a netlink message and send it to the kernel. Right. In order to never ever have to change this again, famous last words, we basically have a netlink CRAD commands. So it's netlink with CRAD, right? You can say create, read, update, delete, or subscribe. You can subscribe to events or publish events, right? And you specify which P4 object. So a P4 object could be specified by a path like that, which is broken down into eventually 32-bit IDs, a hierarchy of 32-bit IDs. And then you put your noun, the blue, the path to the command. And then if there's any object specifics, they'll be in the green, right? So that BNF grammar is everywhere, right? The plus sign, that means I can do more of these. So you have a command to get. You can dump a whole table by leaving out the key. You can create a single entry. You can create a batch of entries. Okay, I can talk to people after if they have questions. You can also write your own applications. We have written basically. We're going to be pushing upstream the TCCLI interface. That TCCLI is going to be querying. So you write any P4 program, you don't have to change TC, right? It generates your JSON file, and then you do a query, and you find it. Or if you're brave, you take the JSON that's generated, write some Python script, and integrate it into your Python script. It's just a name server, essentially, name to ID resolution, right? So one of our goals was we did this. Based on previous experience, people like Vlad and Marcelo have presented at this conference on how they improved TC control path for OVS. And we stole some of the ideas and we added some of our own. So it's we got rid of a lot of locks in the control path. And we've been beating it up with Syscaller for months now to just find bugs, right? So if you're to write an API, there'll be just those 6, 7 commands. And then you pass your ASCII file, your ASCII path, and optionally your data, right? So high performance, I'm going to show some numbers afterwards. So you can write your own proprietary application, but as an open source community, we would like it to be in TC. Okay, so some samples. I'm going to show maybe 2, 3 samples quickly so you can get familiarized with how this would look. So the first one is a very trivial program which will just do a lookup based on an IP address, and then it will replace the source and destination MAC address from the table and send it to a designated port. If it doesn't find the port, it will drop the packet. The second one is, this is the point of what I'm describing here. You can write ridiculous programs if you wanted. Nobody has to see them. You don't have to share them with anybody. So there's somebody, not any of us involved here, who has written a program that does calculate. It's a calculator. It's called an in-compute calculator. So you send it to operands and an operator, and it will do that math for you and give you an answer back. It's silly. Power to them. I mean, and then I can show maybe a slightly more complex example, which is a replacement of the Linux bridge. I'm sorry, Steven. The bridge has 50,000 features now. All interested in broadcast and learning. That's it. So that's all this does, okay? You show that, so if you want to look at where the kfunc is, this is a kfunc here. That part, I don't know if my cursor is visible. That's a kfunc, right? And that's the same kfunc, really. But your key changes. In this case, you're looking at it by destination MAC address. In this case, you're looking up by source MAC address, right? So let me maybe show some example programs here. I'll rush this very quickly. So we can have questions after. Can I have this on, Mike? Oh, it's on. Okay, good. All right, great. I can see this, I think. So let's go to all right, so the first program. Let me just show you the P4 program for it. You could just have said it from there. All right, so Pedro says I have to make the font larger. Okay, so here's your P4 program, right? And I'm going to split the screen into 2 so that I can show what. Okay, never mind. So you define your header, right? This is the DSL, basically. You put together your header, say, okay, here's my Ethernet header, here's my IP header, here's my general header. I'm going to call it my ingress headers. And if you have metadata, if you want to pass foo or bar, this is where you define it. And then you define your parser. Okay, and then you define what I call the control block. So the parser here will be output as a separate eBPF program. I think I should still be able to do this. All right, let me get out of it. I don't know why I'm having a problem splitting the screen. Okay, I'll show the parser separately. But what this is showing is that there is an action called send next hop, which will take a Linux dev, like eth0, for example. It will take a MAC address, so you can enter it as a human being in the hexadecimal options, and it will set the packet's source address to be whatever that action had, destination MAC address, and then it's going to send it to a port you programmed, right? And then there's a drop. This is a built-in intrinsic to drop packets. And then you define your table. You say, okay, my table is going to be looked up by this header IPv source address, which you defined earlier on, right? This header.ipv4. And then you say that's my key basically for the table. And if it matches, I may end up doing a send, next hop, or a drop. That's the control plane program for me. Right? And then this apply means this is like main in P4. Okay, you say apply and you run this next table. So a packet comes in, you invoke the next hop table, and the parser would have constructed the key for you, and then you do a lookup. And if you find it, you may find an action. If you don't find it, you run what's known as a default action, which is to drop. Right? So you're not supposed to look at the eBPF code, but I'll just show you. Okay? So there's two, like I said, there are two pieces of eBPF code here that are compiler generated. One is the parser. Sorry, right there. I never look at it unless there's a problem. So there's your parser. I don't know if I want to look at this, but be my guest, go run this, download the compiler and run it, right? So, and then there's the control block, which is that guy there. Right, so this is the control block. There's an entry point at the bottom. If you attach it to ingress, TC ingress, this is where it will run. I think there should be an XDP one here. I don't know if this was compiled with the XDP in mind. But again, you can see that the code is very mechanical. Requesting about kfuncs. Let me show you one. This one is a kfunc here. Right? It's a table read. You give it the SKB. You pass it some parameters and the key that the parser had already extracted. And note here that every program has what's known as a pipeline ID and a table ID. So you invoke it, it returns you. This is one of those things that it was square hole, round peg kind of thing. But in other words, P4 is match action, but eBPF is not exactly match action, but that's okay. We invoke the kfunc, it returns us the parameters for the actions, as opposed to executing the action. Right? So then we look at if the value is null, then okay, we didn't hit. If it hit, then I guess this could have been optimized. It's the compiler, we can teach it stuff after. So if it says that the action return was a next hop ingress, then we would do the magic of replacing those. Again, this is all compiler generated. If it says to drop, then we will drop the packet, and by default, we'll just say drop the packet, okay? I don't want to spend too much time. And the script that I had sort of described that's also compiler generated will be something like this, right? So you create the program. These are all netlink messages using TC. We just added one command called P4 template. You define your action with, the only thing you define is your parameters and their types, and the kernel will verify them. And then you say, okay, this action is now active. Likewise, you can do the rest. And then you define your table. You say, okay, this is a table with table ID 1. It will do exact matches as opposed to, let's say, LPM or range or ternary. And I'm going to allow it to have up to 262,000 entries. And it will support the following actions. One is called send, next hop, and drop. So if you try to add an entry with a different action, it won't be accepted for this. If you try to exceed 262K entries, it will be rejected. Typically, in software, this is not a big deal, but in hardware, if this was to run in hardware, you would have to make sure that you do not exceed the range that the hardware supports. And then you update it with the attributes and you say, okay, it's ready to go. So at this point, this is ready to go, and you would, let me see if I can find an example of how you would load this. Can you see this, or should I? Okay, never mind. So here's how you'd load it now. You would say something like TC filter action. I'm sorry, I don't know how to make this font any larger, but I hope it's visible. You add it as a filter. You say, I'm going to add a filter called P4, and I'm going to add, that program name is called myprog, which you've already installed through the template. And my first action is parser, the parser that was generated that you've already compiled, and my second action is my program, my control block. Or you can explicitly create it by this way here, where you don't have to say that this is a parser action, but rather a parser object. Or you can do it in XDP. You say, okay, I'm going to run the parser at XDP. Okay, here you go. And I'm going to run the rest at the control block at TC. Okay, for lack of time, I'm not going to show you the rest, but I think, oops. What I'd like to show you is a very ridiculous program, okay? Even I think it's ridiculous, but it's fantastic because it shows the power of what you can do here, right? The calculator program. Okay, I'll just show you the P4 program for it. I no need to show you the eBPF code. So this program, someone decided to invent an Ethernet a header that runs over Ethernet, right here. Right? It takes an operand, another operand, and when it computes, when it does the math, it puts it in the result. That's all. Right? So we can do in-network computing. I know academia is big on this stuff. So, let's use our router to do some as a calculator, or our Datapath as a calculator. Okay, so here's the program. Now you've defined that. You've defined your header. You now define that the different operands, right? You then define your P4 calculator header. You go through that. You define your parser. And then you add static entries. So there's a possibility of being able to say, this entry is static. It means that it can't be changed at runtime. Once I add it to the table, if you try to update from the control plane, it will not work, right? And for lack of time, maybe if someone is interested, please come over to the conference. So once you've added the entry, you would do something like, do I have a good example here? I'm probably not going to show the bridge, but I'll just jump back. Unless someone really wants to see the bridge, I'm not going to show it. I'm just going to go back to the slides if it's okay with you guys. Anybody objecting to that? Nobody. I'm going to do the John thing. Okay, so back to the slides. So the bridge example is this, basically. I didn't show it, but it's a minimalist, right? A packet comes in, you look up, I intentionally call this the FDB table. So you call a kfunc into TC. This is updated through TC, through Netlink, basically. And then is it a hit? Yes. You send to the designated port, right? If it's not a hit, then you check for a register bit that says, okay, I want it to broadcast when there's no. So you send a broadcast to all the ports but the port that came in. And then you check another bit to say, am I allowed to learn from this? You said, yes. Okay, then now you'll call another kfunc to create a table entry. Right, so we are fully stateful, basically. Per P4 spec, okay, we're as stateful as P4 spec says. We do not, let's say, look at ARC sequences or whatever. That's, I'm pretty sure it can be done if, for example, Pensando claims they do it in their hardware. And in this case, you're looking it up by source address, right? So you're learning through a source address. Anyway, I've spent enough time on this. So let me show you some performance numbers. This is on an Intel Cascade Lake CPU, NVIDIA ConnectX 6 card, 64-byte packets on one core, purely on TC, single table, the same example I just showed you, the simple L2, 10 million packets per second. Not very impressive, but I'm pretty sure we can tweak it. It's the compiler generating probably some suboptimal code. We could probably have got better numbers if we ran it on XDP, since it's a trivial example with one table only. But if we used 6 cores with RSS and crafted traffic, so we craft it so that it hits all the 6 CPUs equally, then we can do the 35 million packets per second, which 25 gig 64-byte claims. The control path, like I said, very important for us to make this extremely fast. Okay, so get rid of all the locks, be able to parallelize. These are tricks stolen from the Vlad and Marcelo talk, plus some of our own that we're very proud of. So I would say best case. So in P4, apparently the actions have to be pre-allocated, but we tested it with 2 scenarios where the actions are pre-allocated. So when I add an entry, a table entry, I would use a pre-allocated action. So that's the best case. When I say best case, I mean the fact that we didn't create the action; it existed already. We just pointed to it. And the worst case scenario, we're creating the action from scratch using the parameters that a control plane passes, and we're getting about 463,000 entries per second. It's not exactly linear. We haven't spent time figuring out why it's not linear, but if you take that number and multiply by 4, you'll get a much higher number than 1.78 million. But on these 4 cores, this is a VM, by the way, so I'm pretty sure you can get better numbers on a proper bare metal machine. And the worst case is 1.64, meaning that we're creating these table entries, which then pre-allocate memory for the actions. Now, one thing we didn't do that traditional TC has is we do not attach any counters to the actions. Traditional TC attaches counters, so there is an extra allocation cost there, what we don't incur. Okay. Our testing, this is probably, we're very proud of our testing infrastructure. We got machines that are like running 24 hours a day, especially the syscaller one. That thing has been running probably for the last 6 weeks now. Occasionally it finds bugs. 99% of the time, 99.999%, the bugs have to do with somebody else, right? I can tell you there's a lot of file system bugs, right? We do sparse before we ship syscaller, like I said, check patch. We only recently, with the last patch, which I hope to post after NetNext opens, we've been trying to use strict. Unfortunately, strict gives you a lot of false positives, but if you have 81 characters, it's going to complain about that. We have a CI/CD work using the taxmake. The taxmake guys presented here the other day on the TC workshop, patch by patch. So if we try not to send more than 16 patches, and it will actually compile each one of them separately. This includes IP Route 2, by the way, although we haven't been sending any IP Route 2 code. And then we do 32-bit. We do TDC testing. I would say we have 300 to 400 test cases that have not been upstreamed that are for TDC. And just before we send, we would run it overnight on Coverity, because if you have an open source project and the source is available on GitHub, Coverity will let you test. And we do SMatch and Cosinal. As to further status, like I said, the code has been ready for some time now. I've been posting RFCs mostly to get some feedback, but other than Vlad, who has spent time looking at the patches and added his reviewed by, nobody seems to be paying attention. Please help us by reviewing the patches when we post next. The kernel route code is at that location. The IP Route 2 code is there. Compiler code you can download as well. And we're also working on creating vagrant machines that will make available for someone who just wants to do development as opposed to somebody who wants to run things. And the reason to choose Vagrant is because it runs on Mac, Windows, and Linux. Not my favorite, but we voted on it. Okay. References, there you go. You can look at them afterwards. Several presentations over the last 2 years. This is not what I'm here to present on. The next presentation, so Intel and AMD are both going to present next presentation. There's an integration for hardware offload, but if I was to do hardware offload, this is how it would look. This is our rule in the kernel that you must have an equivalent software implementation. You don't have to implement the same exact algorithms, but an input of X should give you an input of Y on hardware as it does in software, right? So I'm showing like an impedance mismatch there. That's not my problem. That's the vendor's problem. But I would say that P4 is a lot simpler than Flower, mostly because everything is ID based. Like every ID is whatever the compiler generates. And if you use a compiler and you use a vendor backend, in theory, they would update their hardware. And that program here is equivalent to the program that we loaded in the kernel, right? So if I send the value 5 to object ID 3, and I send it all the way to the hardware, will be the same object ID 5 that's in hardware. Okay? I don't need to hard code things like we do in Flower, where every time you want to add an object, and you really don't have to spend I know people have spent 2 years just adding, I can't remember what it was a GTP header on Flower. You have to change IP route 2, you have to change the flow dissector, you have to change Flower, then the driver, and then people will fight you on the mailing list for the next 3 to 6 months. None of that here, okay? And this is how the new Datapath would look like. You could now use the same P4 control to either update the software and the hardware, and you get all the advantages that TC was already offering in terms of continuations of pipelines. So you could put half your pipeline here and another half here. You could put half your table there or another half there, or whatever you feel like, right? And so this has taken years to build in TC. We're going to continue to use that, all right? Status, okay, I'm going to stop here. If there's questions, I still have 8 minutes.
Can you go back to the hardware slide for a second?
Oops. What? All right. Oh, okay. Hey, hi. I'm on video. Okay, that slide. Okay.
So when you said the offloaded program is equivalent to the program that you're offloading in the software, how do you know it's equivalent?
Excellent question. So that's an ongoing discussion right now. So I should have posted that we have bi-weekly meetings. Everybody's invited. Some people show up there. It's mostly vendors. But one angle is to have some sort of crypto signature that gets verified. So there's multiple ways. At this point, by the way, even though I was showing that, the slides have disappeared, but I was showing, can you put the slides back on? Right. I was showing that we had, yeah, there. This is misleading here. Oops, I can't go. Yeah, this is misleading. It shows devlink, but we wrestled Jiri for a long time and we just gave up. So this is not going to be using devlink anymore. There's basically when you load the filter, it's going to go through the kernel now. It's going to go through TC, which will send a message to the driver. I don't know if they'll talk about it in this next presentation. And the driver will use the equivalent of devlink flash to retrieve the binary. So when we send it, we'll tell it the authenticated data of what that file is, so that it goes and loads it. I don't know if it looks like lib firmware. I don't know who knows about how this stuff works.
Well, so let me back up. I think we already had an example of this the other day. So the answer, like you said, signature, but I think let's just call it a SHA one. So find a common ancestor. In this case, it would be maybe the front-end P4 program. Take the hash, give the hash to all consumers, and make sure the hash stays with the program. So when it's compiled into the P4 binary for the hardware, hash is part of it. When it goes into the kernel, the hash is part of it. And then when the kernel wants to offload, yeah, so it's just a matter of querying the driver who can query the device, get the hash, do a comparison. So it can be as long of a hash as you want. Mm-hmm. If they're equal, that should be sufficient to say that the program you're offloading is the same as the program being offloaded. But I think the important thing here is just make sure this is a common problem.
I see.
And we're going to see this time and time again. Anytime we're trying to offload on a separate path from the kernel has to make sure it's the same. We don't want to have to force everything to go through the kernel. So the best way to get visibility, I think, is do the hash. So I think this is just a generic problem, and maybe we should up-level it once and just say this is how you do offloads of complex things by a hash.
Ed, do you know, or Shannon, do you know if when you use devlink hash, flash, is there any signature that gets included? None. You just trust that it's sitting in lib firmware? At this point, yeah. Okay. But I think if we use that mechanism, then it's just a matter of sending patches to them to make sure that it's the same hash. So when you add the filter, when you say TC filter add P4, and you say skip software as well as skip hardware, it's going to go down to the driver. The driver is the one that does loading, not us. And the driver will be passed all the attributes necessary, the name, the IDs, the probably file name, or this is under discussion, unfortunately, still. I don't know if the next presentation will address it at all, but we've talked about it. We've beaten it over like 3-4 times in the last 4 meetings.
Well, yeah, but it might be a separate discussion because, like I said, we want this to be a common solution because we're going to see more and more of these offloads, and if it's not P4, it could be something else. But I think that part of the solution should be common across all systems. It's the way we should do accelerate.
I hear you. Right, I agree. Anybody else?
You said something that I took as maybe slightly negative about things like counters and all the other type of paraphernalia that you expect from, P4 hardware. So do you provide all the stats and everything else like that?
Yeah, that's part of what TC would normally extract out of the. We're not changing any of that, right?
Yeah, but you said something about the fact that you don't do something. So.
It wasn't intended to be negative. I just didn't want this discussion to slide into offload because our patches have nothing to do with offload. Okay. The offload stuff is still going on, and there's a presentation that's coming next. So I said, I'm just trying to put a disclaimer that offload next, nothing to do with this. Right? P4 has value on its own. Is there anybody remote, Felipe, maybe? Oh, there's remote. Okay, put them up, please. Oh, there's no questions or comments. There's a comment? Are they chit-chatty comments or related? All right, forget it then. Right. I don't want to hear about someone's cat. Yeah.
So one other comment, and this might be more along the lines of how you market these patches. And this might be a little bit of a complaint about P4, but I found it hard to find really good examples of useful programs. So you went into that calculator program.
Yeah, it was.
That's completely synthetic.
It's ridiculous. I agree.
So
but it shows what you can do. That's it.
It shows what you can do, but right. And like I said, somehow this just seems like it's more of a P4 marketing thing. It would be really cool if we had a suite of actually useful programs.
Oh yeah.
I think that bridge program, that would be great. And when you
post
upstream,
guys are not going to fight me though. I'm afraid of Steven.
When you post upstream, it'd be really good to have a suite of these are programs that actually work and are useful. Yeah. I think that would give a lot of credibility because when you do the calculate.
Oh no, we have huge number of test cases, but doesn't mean that they're useful. They're testing different things. The compiler has a lot of test cases.
Yeah, but I mean, having a runnable example of a test that does something useful is way more valuable than
do you think
syntax checking and
the bridge one will be good? Do you think?
Bridge or a tunnel or something.
Yeah. I mean, we have plenty, and also, is there anybody online that has a lot of P4 programs that they'd like us to test? Or here? I'm sorry. Is Chris on there? Maybe bring up Chris or somebody who big user of P4. Oh yeah, Chris is here. Okay. Now he lives and breathes P4. Okay, and both in software and hardware. We can't hear you, Chris. Okay, just give us a second. He's setting up the. Thanks. But to your point, while we're waiting for Chris to come on, yes, we will have tons of. Yeah, Chris, can you say something?
Yeah. Hi, folks.
Okay.
Yeah, thanks for the opportunity to talk for a moment. Yeah. So I'm part of the Sonic Dash Working Group, which is an initiative led by Microsoft, and basically it's Dash is kind of democratizing, if you want to think about it, and deploying DPUs or IPUs in the Azure cloud for some really serious applications, where it's accelerating workloads like 100x in terms of performance and scale, maybe 1,000x. And the Dash project, the working group actually, its charter is to model the Dash networking functions in P4, because it's a lingua franca that everyone can read and understand. We actually execute it on the BMB2, but we're actually looking for alternative backends that are more performant and have more features. BMB2 is a little bit dated, and it doesn't provide all the stateful processing primitives that we'd like add-on miss, that kind of stateful processing, which DPUs can actually implement in hardware now on SoCs. So I'm actually responsible for a lot of the automation, the CI/CD framework for compiling and running test cases in the behavioral model. And we would love to have another backend. And right now we're exploring P4DPDK. There are some gaps in its implementation, but it's really close to being able to run Dash code. And this is serious network application. So if someone wants to look at the Dash or the Sonic Dash, the sonic.net, I think /dash project on GitHub, you can see some, interesting tunneling applications and ACL applications. And I'd love to see that run in P4TC.
Yeah, and we will be using Dash as a test case for us. Anyway, I've run out of time. I'm sorry. I've already exceeded apparently by 5 minutes, I'm told. So there's going to be a TC workshop, extension today. Please maybe, or catch me in the break or whatever. I thank you for listening.